So moles are great, but we can't measure moles physically. So what we need is masses of reactants and masses of products. Well, we've already learned how to convert between grams of a substance and moles of a substance. The conversion factor is the molar mass. And from moles to grams, the molar mass. What we just learned is how to go from moles of one substance to moles of another substance using the ratio from the balanced chemical equation. And this is the generic path for stoichiometry problems. There will be some variations, but this is what you should remember. Grams to moles, well, let's just use abbreviations if we're going to use abbreviations. Grams to moles to moles to grams. Chant that to yourself. Grams to moles to moles to grams. Grams to moles to moles to grams. Grams to moles to moles to grams. It's never moles to grams to moles. The moles are in the middle. Moles in the middle. Grams to moles to moles to grams. What mass of carbon dioxide is emitted by an automobile when 5.0 times 10 to the 2 grams of pure octane is burned? There's a balanced chemical equation. We can tell this is something combusting, right? Reacting with oxygen, forming CO2 and water. So this number, 5.0 times 10 to the 2 grams of pure octane. Eek! We don't know what the formula for octane is. Well, this is oxygen. That's not octane. That's carbon dioxide. That's not octane. This is water. That's not octane. Guess which one is octane? The other one. Okay, process of elimination. That's called putting on your thinking cap. I wish they actually made those because I'd buy a classroom set of them. Wouldn't that be good? Oh, I can think now. Okay, 5.0 times 10 to the 2 grams of that thing. What are they questioning us? What are they asking? What mass of carbon dioxide? So here's carbon dioxide. So I'm going to write my question mark under there. And it's the mass, so the unit should be grams. Everybody okay with that? So now, this is my starting point, the thing I have a number for. This is what I'm going to, the thing with the question mark. I have to figure out how to get from here to there. Grams to moles to moles to grams. So grams of what I'm starting with. So we're going to start with grams of C8H18. And I'm going to convert to moles. Moles in the middle. I'm going to convert that to moles of the same substance. Then I'm going to convert to moles of the thing I'm trying to learn about. Moles of CO2. And then to grams of CO2. Grams to moles to moles to grams. There are no shortcuts for this. You learn the pattern, and once you get it, it doesn't take that long. So I have a path now. I'm going to follow the path, and my equation is going to have how many fractions in it? 2 plus 1. There's arrows, right? 1, 2, 3 arrows, 3 factors. 5.0 times 10 to the 2 grams of, write the formula. I know it's tedious. Do you know how many times I have done this particular problem? A lot. Sometimes 2 or 3 times a semester. Okay, what's the next one? It's moles of that. And what's the next one? Moles of CO2. Now I'm just copying down what I figured out. Okay? Grams to moles to moles to grams. I want to take this unit and put it in the denominator to make the units cancel out. This is the same thing I've been teaching you about dimensional analysis all semester. This is going to be moles of C8H18. So those units cancel out. And down here, I'm going to have moles of CO2, so the units cancel out. Units first. Put all the units in first, then put the numbers in. When you get good at it, you can mix it up a little, but for now, put the units in first. I like to do the moles in the middle because that one's easy. I like to do that one first. Because I don't have to do any calculating, I just have to look at what's in this equation. 2 moles of octane. So I'm going to put a 2 in front of octane. 2 moles of octane. How many moles of CO2 would that make? 16. Do I have 16 moles of carbon dioxide? Do I have 2 moles of octane? I don't know, but this is the ratio in which they combine. The first fraction and the last fraction are molar masses. What I do on an exam to make these questions go faster, because there's a sort of limited amount of time, is I'll give you the molar masses so you don't have to calculate them. But on all the problems, we're going to have to calculate them. So for C8H18, 8 times the mass of carbon plus 18 times the mass of hydrogen. 8 times 12.01 plus 12 times, no, not 12, 18 times 1.008. Okay, 114.224. You can say that that's grams is equal to 1 mole, or you can write it as grams per mole, whatever makes the most sense to you. The number is the number of grams in 1 mole of octane. Now, for significant figures and these molar masses, the best thing is, bless you, just write down what your calculator shows you. At most, it's going to be 1 or 2 extra digits. It's not going to cause a problem. We could argue back and forth about the sig figs, but it's not going to end up mattering, because how many sig figs are in the starting mass? 2. No matter what you do to that, it's going to be more. It's not going to limit, so we don't even have to think about it. This is exact, and if we just put down all the digits that we get when we calculate this mass, then we don't even have to worry about it. So that's 12.01 plus 2 times 16 equals, and it should be 44.01 grams per mole for CO2. But do not round your molar masses any less than 4 sig figs. 44.01. Now, start at the left, go across, multiply by the top, divide by the bottom. Feel free to ignore the ones. So I've got 5EE2 divided by 114.224 times 16 divided by 2 times 44.01 equals. So my answer should have 2 significant figures. So there's the first 2, 4, 1, 0.1, and it keeps going. The unit is gram. I need to be careful when I round this. So I'm keeping this digit. This is the hundreds place. The next digit is the decider. It tells me, do I round up or round down? This is a 4, so I leave the 5 alone. I leave the 5, I've got the 1 and the 5, and then I have to replace these digits that are before the decimal point. I have to replace those with zeros so that I don't change the size of the number too much. 1,500 grams. A better way to write that is to put it in scientific notation. I'll stick it up here. 1.5 times 10 to the 3 grams. That's the best answer. Any questions? 15 is not a good answer. It's a very, very bad answer. It's a wrong answer. 15 and 1500 are not the same thing. What mass of octane would be needed to generate 42.3 grams of water? So the last one, they gave us information, a mass of octane, and asked for a mass of CO2. Now they're giving us a mass of a product and asking for mass of a reactant. It's exactly the same process. So I've got the question. I'm going to take the number and write it under my equation. That's water, so I've got 42.3 grams of the water. The question is what mass of octane? So under octane, question mark, grams, because it's mass. Grams to moles to moles to grams. Grams of water to moles of water to moles of what I'm trying to find. I can go directly to this. I don't have to pass through these things. It's like going directly to jail. Don't pass go. Don't collect $200. Moles. C8H18 to grams. It's always moles in the middle, like Malcolm in the middle. Okay, so 42.3 grams of water times and a line. So the next unit is moles of water times and a line. The next unit is moles of octane times in a line, grams of octane. I take the grams of water, that becomes the number, the unit, in the denominator of the next term, so they cancel out. Moles of H2O. Moles of C8H18. These stoichiometry problems, in many ways, are simpler than the dimensional analysis unit conversions that we did at the beginning of the class, because the path is so very similar from one to the next. It's always grams to moles to moles to grams. It's just a matter of which substance is the starting one, which is the ending one. You're going to have a mole ratio from the balanced chemical equation, and you're going to have a molar mass for one thing and a molar mass for the other thing. It's very repetitious. Okay, so the middle one is my favorite because it's the easiest. So in front of octane is the number 2, so I'm going to put 2 here. And in front of water is an 18, so I'll put an 18 there. These coefficients only are used in the mole ratio, mole to mole ratio. Don't use them anywhere else in this. Now I want to know what the mass of 1 mole of water is. So that's 2 times 1.008 plus 16, 18.016 grams per mole. And then octane, can't quite remember. Oh shoot, no, I can't even go there. Okay, tell me what it was. It was like 116.224? 114.224, thank you. We just calculated that. There's no point in doing it again. I just can't look back. Any questions? Yes?
Why wouldn't the first mole of water be 18 moles?
Okay. Well, we can't say that there's 18 moles per 18.016 grams, right? Because 18.016 is the mass of 1 mole of water. Yes, there's an 18 here, but if I want to put an 18 here, then I'm going to also have to multiply the denominator by 18, and that's a lot of extra work.
Also, does moles per gram is the...
Moles per gram, this is the molar mass. Molar mass is the mass of 1 mole. We get that by looking at the chemical formula. You know, the H2O. There's 2 moles of hydrogen, 1 mole of oxygen in 1 mole of this. This is 18.016 grams per 1 mole. So it's 1 mole per 18 grams.
So earlier, did you say the second conversion ratio and the last one are the molar masses?
This is the molar mass, and this is the molar mass. The coefficients, the 18 and the 2, are only used in the mole-to-mole ratio. This one in the middle. Don't stick them in here. It's very tempting, I know. It's tempting to stick a 2 down here. And if you're really careful in how you do it, if you also multiply this by 2, you can come up with the right answer, but it's a lot of work, and it's completely unnecessary. So we use the 2 and the 18 once in here. This is a molar mass, the mass of 1 mole. This is a molar mass, the mass of 1 mole. So we go start at the left and move across. 42.3 divided by 18.016 times 2 divided by 18 times 114.224 equals. It's almost always the starting number that's going to limit your sig figs. The mole ratio is exact, and your molar masses have at least 4 significant figures, so we can just kind of not worry about them. So 29.7, write down 2 extras, that many grams of octane. And then when I round that to 3 sig figs, I get 29.8 grams. 29.8 grams of octane would produce 42.3 grams of water. Now when you ignite your gas stove, we have combustion going on, water is being produced. Do you see water getting all over the place? No, because it's hot. It's produced in the gas state. If you light that burner and far above it, and you're welcome to try this in lab, it works with those burners too, you hold something that's cold, maybe a cup with ice in it, or even a cup with just water in it, it'll cool it down. As it hits that cool surface, the water condenses. That water came from the combustion of the natural gas. Let's do another one. Magnesium hydroxide, the active ingredient in milk of magnesia, neutralizes stomach acid, primarily HCl, according to the reaction. Okay, this is backstory. We don't need that. It's just to make the problem more interesting or more relevant. Here's the equation. How much HCl in grams can be neutralized by 5.50 grams of magnesium hydroxide? Take the numbers and write them under the formula, or the balanced chemical equation. So I've got 5.5 grams, 5.50 grams of that. The question, how much HCl in grams? So here's HCl, question mark, grams. What's my generic path? Grams to moles to moles to grams. And so maybe by this point we can just jot that down, grams to moles to moles to grams, without necessarily writing all the formulas in there. This is what I'm starting with. This is what I'm ending up with. So I'm going to start with 5.50 grams of magnesium hydroxide times and a line. I'm going from grams to moles. It's going to be moles of the same thing, because we can only change one thing at a time. I'm changing the unit from grams to moles, but I'm still talking about the same compound. Next is moles again. So this is moles of what I'm trying to find. Here I'm keeping the unit the same, and I'm changing the compound that I'm talking about. And then at the end, grams of HCl. If you need to write the formulas in here, grams of magnesium hydroxide to moles of magnesium hydroxide to moles of HCl to grams of HCl, by all means do that. I'm getting tired of it. My feet hurt. Okay, so I've got my path units on top, and then I fill in the bottom so the units cancel out. And I understand it's tedious to write all the chemical formulas in there, but it is important, because otherwise you can get things twisted around and you won't even recognize that that's happening. So those cancel, these cancel, and those cancel. Again, I like to start with the one in the middle because it gives you a kind of a boost to just like knock that one out. So this comes from the coefficients in the equation. There's one of the magnesium hydroxides for every 2 HCl. I need 2 moles of HCl for every 1 mole of magnesium hydroxide. Now I need molar masses. So magnesium, 24.31 grams. And it's OH2. So I've got 2 oxygens and 2 hydrogens. So 24.31 plus 2 times 16 plus 2 times 1.008, 58.326 grams per mole. Again, the easiest thing is just to write all the digits in here. It's not going to hurt anything. And then I need the molar mass for HCl. That's a little simpler. 1.008 plus 35.45. It ends up being 36.458. Grams per mole. 5.5 divided by 58.326 times 2 times 36.458 equals. Starting number has 3 sig figs, so my result is going to have 387. Write down 2 extras, round it. There we go, 6.88 grams of HCl. Doing mass-to-mass conversions like this is something you should devote some effort to and get it down so that you don't have to think about it too much. Because this type of calculation comes up over and over and over and over again. It is central to chemistry. It's really, really important. So many of these. Okay. One component of acid rain is sulfuric acid, which forms when SO2, a pollutant, reacts with oxygen and rainwater according to the following reaction. Again, that's backstory. Assuming that there's more than enough oxygen and water, how much sulfuric acid in kilograms forms from 2.6 times 10 to the third kilograms of SO2? Okay, let's write this down. So I'm given this number of kilograms of SO2. So I'm going to write that under the formula for SO2 in the equation. 2.6 times 10 to the third kilograms. Okay? In the question, how much H2SO4, so over here is H2SO4, question mark, It wants kilograms. So generic path, grams to moles to moles to grams. Grams to moles to grams. But we don't have grams. We can convert kilograms to grams. Okay, so we can add a step on to the beginning, kilograms to grams, and then put a step on the end, grams to kilograms. Oh, yeah, that's what I say too. Like 5 of them now? Let's think about this for a minute. If I'm converting from kilograms to grams and from grams to kilograms, aren't those the same conversion factor, just opposite of each other? I think those are going to cancel out. So let's do this. We need to be careful, but let's just do the regular thing and see how it works out. Okay? So I'm going to write down at the beginning here, I'll start on the lower line, 2.6 times 10 to the third. Now what I'm going to do is I'm going to write the kilo in a different color. Kilogram. Just kind of draw attention to it. It's there. Kilo is a multiplying factor of 1,000. Right? A kilogram is 1,000 grams. So I could cancel gram without canceling the kilo. That's possible. So we're going to leave the kilo there and kind of ignore it for now, but it is there. So next is, oops, I forgot to write kilograms of what? Kilograms of SO2. Very important. And then I'm going to go to moles of SO2. And then I'm going to go to moles of what? H2SO4. The thing where the question is. That thing. And from moles of that thing, I'm going to go to grams of that thing. So I'm going to put moles down here. H2SO4. And moles of there's no HCl here, moles of SO2. And normally I would do grams of SO2. Okay, so here I have grams of SO2 and kilograms of SO2. Let's just cancel the gram and leave the kilos sitting there. So I'm canceling this part. I'm not canceling out the kilo. It's still there. It's red, right? So we'll go about our little bumbling business here, finding numbers. So moles in the middle, 2 moles of SO2, 2 moles of sulfuric acid. Now I'm often asked, well, can I cancel those out? Sure you can. If you want to simplify that ratio or cancel things out, that's fine. I'm thinking, I'm going through on my calculator, it's less thinking and not many more steps to just multiply by 2 and divide by 2. It's not going to hurt anything. I need the molar mass for SO2. Sulfur, 32.07, plus 2 oxygens. I think that's 64.07. So 1 mole of SO2 is 64.07 grams. And then sulfuric acid, 2 times 1.008 plus 1 sulfur at 32.07 and 4 oxygens. So 2 times 1.008 plus 32.07 plus 4 times 16 equals 98.086. 98.086 grams of sulfuric acid to 1 mole of sulfuric acid. So I got all the numbers in there. Okay, let's go back and look at our units and see what's going on. So we canceled these guys. I canceled this gram of SO2 with that gram of SO2, but I've got this kilo left sitting there, and then I've got grams of sulfuric acid over here. Kilo stands for 10 to the third. It's just like a factor, a variable, right? It doesn't necessarily mean it's only, I can't just use it on SO2, I could use it on anything. So this is still sitting here, and I've got gram, and so my unit ends up being kilograms. Well, that's convenient. I knew that was going to happen. 2.6 times 10 to the third. 2.6 EE3 divided by 64.07 times 2 divided by 2 times 98.086 equals, I should have two significant figures, 3980.3, and it keeps going. So when I round, I need to be careful. Yeah, this is going to round up to 4,000, isn't it? This is the decider. The 8 tells me I need to round the 9 up to a 10, which rounds the 3 up to a 4. So I get 40, those are my sig figs. And then these places here before the decimal point, I have to replace them with zeros. And there I've got my kilograms. There's not a good way to indicate that the first 0 is a significant figure and the last 2 are not, other than scientific notation. So this one you really should put into scientific notation, 4.0 times 10 to the third kilograms. Yes?
Could you mind explaining once more why the kilograms and grams would cancel out? Because couldn't you just go convert kilograms to grams and then plug it in?
Yes, you could. You could convert this mass in kilograms to a mass in grams and then stick it in there. And then the number that comes out here, you're going to have to convert back to kilograms. That works. And if you want to do that, that's absolutely fine. I just want to show you that you can treat the prefix here as its own thing. And you can cancel the gram without canceling the kilo.
How would putting it straight into the calculator like that, get you to grams?
Another way to think about this in terms of canceling stuff is you can think of, well, this gram is canceling that gram, and that leaves kilograms as my final answer, my final unit.
Oh, is it because the prefix and the prefix multiplier are already together?
No, no. Here, let's do this. No, there's nothing to be sorry about. So we could take 2.6 times 10 to the third kilograms and convert that to grams. And then we could go to moles and grams, and then we've got moles and grams and moles. And then the moles are going to cancel, the moles are going to cancel, the grams are going to cancel, the kilograms are going to cancel. And then we're left with, if we put the numbers in and do the calculation, we get an answer in grams, but we have to get it into kilograms. And so at the end, we're going to convert to kilograms. So that those cancel out. And what I'm trying to show you is that this at the end and that at the beginning, those cancel out. Right? We multiplied and then we divided again. Yeah.
Isn't it because like the order you multiply numbers in doesn't matter?
Yes, the order that you multiply numbers in doesn't matter. So I could put this first and then put this right after, and it would seem more ridiculous that I'm multiplying by 1,000 and then dividing by 1,000. So if the way I did the problem the first time doesn't make sense to you, if it bothers you that I did that thing with the kilo, then do it this way. There's nothing wrong with this except it's longer. And if you're bad at converting kilograms to grams, then you've got 2 opportunities to screw it up. If you screw it up the same way, they'll cancel out, but if you screw them up 2 different ways, then you're in more trouble.